Hello, everybody. Thanks for attending this presentation. Uh, I guess all of us would hope to do this offline at the UCLA Center, but I think we maybe should just settle today to have this online. But that's okay. I hope we all have a good time, and please feel free to ask me any questions on the chat, or at the end you can just unmute yourself and ask a few questions. So the presentation today is about a paper I wrote with a few collaborators. So I'm Adriano Koshiyama. I'm a research fellow in the computer science department. I started my postdoc in April last year. Sorry, this year, and I'll probably be around in the department for the next years or so. This paper was basically the last paper that composed my PhD thesis. I wrote this with Sebastian Flanehag, he's now in DeepMind, Stefano, which is still around the UCLA Center. Some of you know him. He's quite a character. Nick Firozi, which is my co-supervisor, and Professor Philip, which was my main supervisor. You can find this paper on arXiv, and so you're gonna find this copy over here, and it's probably describes better, and it's probably more, let's say, mathematical and more interesting than actually my presentation will be. I'll try to boil down and show more diagrams and try to wave my hands and make you understand what I'm trying to do, but feel free to ask me any questions anyway. Good, so let me just, yeah, perfect. I think it's probably a better preview. So let me start, and I'll try to do this presentation half an hour, so we're gonna have enough time for questions and answers. Good, so what we are gonna do today, so I'm gonna do a quick summary of the whole paper in 3 slides, in case you just wanna drop out and go do something else. And then, but if you decide to stay after I tease you, I'll go through and show the motivation. I'll try to talk a little bit about what is transfer learning. Maybe some of you know already. Maybe some of you don't know already. I would say that most of you in the UCLA Center know about transfer learning in one way or another. Maybe with different names, maybe with different ways to do it. But I'll try to talk a little bit about it as a concept. Then I'm going to show my actual model called QuantNet, which is probably maybe the first pre-trained model for financial time series. So I'll show more or less how it works and show some results and the key contributions that I believe our paper had. Good, so summary, very simple. Some of you, I guess most of you who are doing foundational research or maybe doing research on NLP and some other topics, you probably have not much idea about finance or how financial markets work or even how a bank works. So just to give a quick overview, you have a bunch of markets. Maybe SPX means S&P 500, UKX means FTSE 100, SACEDX is the index for Saudi Arabia. So imagine that you are trading across the globe. So you have different markets, and let's say equity markets, just to simplify. So you have all these markets with all these time series and all these assets. And how actually it works in a bank, you have a bunch of people, from traders to salespeople to quant strategists to research to quants. All of them, in a way, they work together with portfolio managers to try to find strategies, indices, ways to make some bucks trading assets, maybe in a specific market, maybe doing pair strategies, which is basically buying and selling pairs of assets in different markets. There's so many different ways of making some bucks in this market, okay? So, but the key idea is that all these individuals, all these teams, they are all looking at markets, they're looking at the data, and they're trying to come up with something that we call a signal. A signal is basically how much I should buy or sell of a specific asset. Okay, people would say how much should go long, how much should go short in a specific asset. Most cases, they tend to normalize this between 1 and -1, meaning 1 you buy a unity, -1 you sell a unity. Anything in between is basically fractions of that asset. And of course, that could form a portfolio afterwards when you have multiple assets. Okay, so the idea is that you get all the data from different markets. Those individuals there do some computation, do some organization, etc., and they end up having trading signals that is going to define how much you should purchase of a specific asset on a specific market. Okay, that's the problem we're trying to tackle, and what we're trying to do is to go a little bit beyond that and replace all of those people in between by a machine, of course. And this machine will basically look at the data across different markets, encode this data into a abstract representation, do some mapping or some transformation inside this abstract representation, and then map it back, decode it back to the market in form of signal. Okay, so in a way, what we're trying to do is replace all those activities in between by a fully end-to-end global trading strategy, where this global trading strategy is going to look at patterns that you can see specific to markets, so idiosyncratic features of every market. So if you're trading in Brazil or you're trading in Argentina, there's probably some patterns of those markets that is local. But at the same time, this strategy will try to look at a global perspective and find patterns that repeat itself regardless of which market you're playing with. Or maybe, not I would say not even a global, but more sometimes even in a regional point of view. And we know, based on multiple studies and multiple research across different domains, that there are characteristics that, for instance, emerging markets like Brazil, Indonesia, China to some extent, and some Latin American countries and some other Asian countries have that make them different from the developed markets. So like US markets, UK, Germany, and so on. So there is characteristics that segment those markets. And one of the interesting things, and I'm going to show this for you in the results, is that QuantNet, which is the solution, we're able to, by itself, by just looking at the data, discover the segmentation across the globe. We look at 58 markets, and we found the segmentation, funny enough. So just in a nutshell, we evaluate this strategy, this fully end-to-end strategy, across 3,000 assets, more or less, and looking at 58 global equity markets. So we look Latin America, North America, Africa, Middle East, Europe, Asia, Pacific, look at a lot of markets, and we compare our strategy with the, let's say, the benchmarks that people would use more in the finance literature, cross-sectional momentum, and some other strategies similar. We beat them up by 50%, 69% margins, which is quite big. And when we compare our strategy towards a non-transfer-based strategy, we have improvements of the order of 15 to 41% improvements. So doing some transfer helps you get better results, even though you're not necessarily using so much information. That could be interesting when you're trading, for instance, using news. Some people would use news. Some people would use tweets even. But if you just look at historical data, historical prices and returns, if you just use that information, you can get improvements by performing transfer learning. So our key contributions are a novel architecture for transfer learning across trading strategies, a novel learning objective. We propose to use Sharpe ratio as the objective function. That's probably the first time someone has done that. And funny enough, there is a good body of literature that points out that if you want to do trading, you should use Sharpe ratio as the objective function, not, let's say, RMSE, which would be the typical one that people would use. And the last point is that we're able to provide or achieve significant improvements across global markets just by doing this end-to-end learning system. Okay, that was the summary. Let's start the presentation. So what is the motivation? The big motivation is the challenge in itself. And the challenge has two components. One is the size, another one is complexity. I think size is very easy to sell you. We are dealing with a problem where there's a lot of money invested in it. So a good chunk of all the FX market is done by one way or another, some kind of algorithmic trading system. Trading strategies being used a lot in equities nowadays. 80% of the trade volume in equities are done by some kind of trading strategy. Maybe now with the rise of Robinhood, maybe a little bit less, but still a good chunk of that is done by a trading strategy. And probably there's a lot this is a very conservative estimate. It's $500 billion in asset under management. I would say there's even more that's done by some kind of systematic financial trading strategy. Why it's so difficult to build trading strategies across markets? Specific market, not much, but in a global scale. The big problem is that although you have data, so data is not a problem, the big issue is that it's difficult to put the data together. So you cannot consolidate the data so easily because the markets, they are not homogeneous. You have different assets. US market has some assets that are trading since the beginning of the 20th century. Where you go to, let's say, Brazilian market, there's some stocks that are starting 10 years from now. Even in the US market, every month there is an IPOs coming in, and you have recently you had Palantir. Palantir has probably 2 weeks of trading data. So you have all these problems where you have assets with different size in terms of the time series. The problem also gets bigger in terms of complexity when you add the new markets, particularly when you add markets that are too far away to each other. So if you're trading India and if you're trading US, it's more complicated than you're trading UK and US. And the problem is because you cannot put the data more or less together, consolidate them, very complicated. And even if you can consolidate, you end up with this massive number of assets. Those two problems, they compounded a third one, which in the financial community, people would call backtest overfitting. But let's say the AI community, the machine learning community would just call overfitting. And the big reason is that it's very easy. And that's the big problem in finance. And that's one of the big pitfalls that we see in a lot of papers in this realm. They propose a new trading strategy or a new way of trading or way of making some cash, etc. But the results are all overfitted in the sense that they were not able to provide a good way to pursue model validation. Time series is a bit complicated, and I guess some of you who do NLP, etc., all deals with this problem of sequence. And time series is a sequence data problem. There is some other particularities and a different way to do validation, particularly when you're playing in this domain, which is finance. Okay? Have a size problem, have a complexity problem. The current solutions are, as I mentioned, maybe consolidate all the data in the same spreadsheet, let's put it this way, or in the same database. That doesn't work for all those reasons I mentioned. Maybe just build market-specific strategies. Just build one strategy for UK, another strategy for the US, another one for Brazil. Off you go. Yeah, that's what people have been doing mostly. And the third one is to try to build some kind of market-agnostic strategies. That's also a possibility. So you have strategies like cross-sectional momentum or time series momentum, where they are kind of more generic strategies where we can apply this to a lot of markets at the same time without much consideration about particularities. That's a possibility, and people have been using that. We propose another one, which is using QuantNet. And the big idea is that we will try to encode the different markets into a representation, a unique representation, where we will have this transfer layer, and this transfer layer will do some mapping in it. And this mapping, this transfer layer, will be responsible to provide some global context, differently from the encoder and decoder layer, who are more focusing on market-specific context. Okay, we do that, and the idea is that we also try to incorporate multiple losses into a single network. And when you do that trick, you improve regularization and you avoid the overfitting problem. Our key goal is to try to avoid the overfitting problem. And by doing the transfer learning components, we can not only fix the situation of having multiple markets, but you also benefit from that because of the transfer learning element to it. Good, so let me talk a little bit about transfer learning before we go. There are like hundreds of images that you can Google, and they will tell you more what is transfer learning. A very good paper that you can find, there's even a book now, which I have over here, funny enough, I can even pick here, sorry. There's even a book here called Transfer Learning. It's a recent book, 2020. You should definitely have a look at it if you're interested. It's done by these two authors who wrote a review paper a few years ago. It's a very famous review paper. So if you type review transfer learning, it's probably the first result you're going to find in Google, which is Pan and Young. And they wrote this book 2020 recently, where, fun enough, when they were writing the review, if you look at the review exactly, this deep learning revolution is not featured there, of course. In this book, there is more the deep learning component. But the big idea in transfer learning, different from meta learning or traditional machine learning, is that in transfer learning, the key goal is to share knowledge across models that are facing different tasks. Okay, so in traditional machine learning, someone gives you a data set or gives you a simulator, and then you're going to learn some model based on that. And then when someone comes in with a new data set or a new simulator, you learn another model for it. So you don't, and every time that you're doing that, you're kind of starting from scratch. Maybe there is some transfer that is happening based on you, because you are, as the human, you're being transferred to a new problem. But in terms of the model that you learn, you're not transferring it. The models are bucketed, they are encapsulated to specific problems. So transfer learning tries to bridge the gap. Transfer learning says, cool, instead of us all the time starting from scratch when a new data set comes in or a new simulation environment comes in, let's try to find a representation, a way to bring the knowledge that we garnered from one task to another one. So we can always, instead of starting from scratch, we can start from a good prior, as my Bayesian friends would say, and try to tackle that problem going forward. that is becoming nowadays the, funny enough, the paradigm that will probably turbocharge all the models going forward. This paradigm of traditional machine learning, of getting the data, doing hyperparameter tuning, going forward, I think it's just going to collapse, and we will be doing more and more transfer learning as we go forward. So we have like task-specific models. We're going to discuss this a little bit more later. The cousin, or maybe even the dream of a transfer learning, is to do meta learning. Maybe I should talk this about some other time, but the key goal in meta learning is not transferring much the model itself, but it's transferring the way to learn, which mainly means transferring sometimes the optimizer, or transferring some other element that led you to learn a particular model. So you're trying to find a fine-tuned optimizer for specific tasks, and then hopefully for a bigger one. It's pretty much like replacing gradient descent for another kind of task-specific optimizer. Good, so that's the big view about transfer learning. Transfer learning assumes multiple forms. I'm even missing one here. Maybe you can put it under the sequential transfer learning umbrella, which is something called federated learning. The key idea in transfer learning is that you have this thing that we call domain. And the domain is basically the feature space. And the task is basically the conditional between the label space and the feature space. And the key goal is that you have a source domain and a source task, and a target domain and a target task. And it is that you try to learn something on the source domain and in the source task that you are able to move or transpose or transport to the target domain and task. Okay. There are different forms, as you can see here. What we're going to be doing in this paper is sequential transfer learning. But if you're doing multitask learning, you're doing transfer learning. If you're doing few-shot learning, you're doing transfer learning. Zero-shot learning, you're doing transfer learning. Domain adaptation, you're doing transfer learning. Concept drift, you're doing transfer learning. You can put everyone in the same umbrella to some extent. Just to give you a quick example for one of them, concept drift. The idea is that you are trying to model the conditional distribution that is maybe changing when you are going forward in time. And there are different regimes where this conditional distribution is changing over time. It can change on abrupt manner. So, sorry, pictorially describing this, you know, the circles, the green circles are becoming blue stars all of a sudden. Gradually means that you're seeing more blue stars coming in as the timing goes by. Incrementally, the circles are morphing into stars. Recurrent is when you're seeing flipping stars and circles, and blip or outliers means sometime a star pops up. These are different ways to perceive drifts happening, and there's a massive body of literature with different ways to detect and prevent concept drift. Detection sometimes means tracking the error across time. There could be a strategy to detect. Another strategy would be to try to model this conditional relationship and then track it over time. That's another one. To prevent, there are different offers. There are also some argue for ensemble strategies, or there argues for a combination between detection and online learning. So different ways, different forms, but interesting enough, there's quite a few solutions if you're interested in this domain. One that very widely used is multitask transfer learning. And the big idea in multitask transfer learning is that you are going to learn a single model that in parallel we try to solve all the tasks available, and we will enforce, by solving these tasks, we will enforce a full to partially shared representation. So sometimes maybe the input layer is not fully shared, maybe it could be partially shared. The transfer layer, let's say, maybe it's fully, maybe partially shared. Sometimes it differs, but it is that all of them will be done concurrently, done in parallel. And when you aggregate the objective function, it's another problem in multitask transfer, which is how much weight you should put across different tasks. You know, when you are going to combine the loss function across tasks, some people would just basically take an average and off they will go. But there's some other alternatives for that. But it is that you have a fully shared representation when you're doing multitask transfer and you're solving all the tasks at the same time. You're producing predictions for all the tasks at the same time, etc. It's a bit complicated when you want to add another task here. So if you have a new task, it's a bit more tricky to add it or to make the transfer to actually happen. So alternative for that is to use something called sequential transfer. Sequential transfer, you have you try to learn in a sequential way each task by basically using some kind of encoder for, let's say, task one, mapping the inputs from task one to a representation, applying the mapping that is being embodied in the transfer layer, and mapping back to the task through a decoder. And then you're going to receive a error feedback or some kind of reward, and then you update the decoder, you update the encoder, and you update a little bit the transfer layer. And then you move to the second task and you repeat that. So the second task, you do the same process, you pass through the inputs, you encode them. When they are in this abstract representation, you apply some mapping that is embodied in the transfer layer, and then you decode it, get a prediction, computer loss, propagates back, updates the decoder and the encoder, and updates a little bit the transfer layer as well. So you can see the transfer layer is the only layer that is shared across all tasks, but the encoder and the decoder, they are just specifics for the tasks, okay? And it's very straightforward to add another one. You can easily add another task. The only thing that you need to add is a new encoder and a new decoder. So if a new market pops in, you can just basically easily add that. There is a mix of, that's something to be argued about. There's a mix of meta learning in this, but I don't want to go much into that. I would rather stick with our discussion here on transfer learning. Okay, that's the, let's say, the more abstract discussion on transfer learning. What about the ways to perform transfer, right? There are 4 approaches that you're going to find in the literature to perform transfer. The first approach is the instance-based approach, where you simply reweight labeled data in the source domain, so you can use it for the target domain. So you're basically changing weights in for every data point that you have in your source domain, so you can use it, you can reuse it on the target domain. Another one is to do the feature transfer, where you find a suitable mapping from one domain to for the source domain to the target domain, or maybe from the source task to the target task, but usually it is from the source domain to the target domain. And this feature transfer, back in the old days, people would do canonical correlation analysis, or they would do PCA on both domains, and then they would use the PCA as the shared representation multiple ways. Nowadays, and probably the most commonly used and adopted by the deep learning community is parameter-based. And the idea is that you're trying to learn a shareable representation or shareable parameters or priors that you can share between the source and target task. I'll discuss a little bit more in the next slide what is the parameter-based approach. But the more, I think the more visible one is when people use, for instance, BERT or even GPT-2 or nowadays GPT-3 as well, but BERT particularly, when they simply go there and they use a pre-trained BERT, they shave some of the layers off, and then they replace these layers they shave by the layers for their problem, but they're using a good body of parameters there for that model. Let me just show you quickly the feature-based approach. There's even a good paper from Pontil, on this topic. That is that you're transforming domains, both domains, from the source and from the target to a common latent feature space, usually low dimensional. Or you can transform from the source domain to the target domain. So you transform both domains to a unique one, or you map from the source to the target one. And this could be done via some kind of encoder that you're going to learn, or some unsupervised technique. There are different ways to perform this feature transfer. But when you do that, now you have a bigger data set. That's the idea. And then maybe potentially you can easily do some kind of semi-supervised learning as well as part of the process. So you can even improve the accuracy of your model. The other way is to do parameter-based approach. So the key idea is that you pre-train a model. Let's say you pre-train a BERT, as Devlin did with a lot of data from Wikipedia and some internet sources. So you pre-train a model for a generic task, and then you fine-tune this model to specific tasks. So you can fine-tune the model for SQUAD. SQUAD is a Stanford question and answer data set. That's a specific task, and people in the NLP community, and we have a big NLP community in the AI Center, could be one approach that they do to improve question and answer pairs. You can do that for, there is one in finance called FinBERT, which is an application of BERT to finance and so on. So the pre-training and fine-tuning goes hand in hand. So you pre-train a model for generic task, then you fine-tune this to your specific task. And this is being used a lot by the NLP and computer vision community. Let me talk about my model quickly. So just before we talk actually about the model, just some specifications, some notation. What is a financial market? Financial market is basically a concatenation of assets. You have any assets in specific markets. The market's I, the asset is J. You have any assets for MI. Every time step, we have access to a vector of excess returns. So for every time point, for each asset, we have we are able to sample the returns. Okay. What is a trading strategy? A trading strategy is a function that has some parameters data, and a trading strategy basically is going to look at the returns for maybe one asset, maybe the whole market, and try to come up with a set of trading signals where the trading signals will constitute what is called the market portfolio. So there is a market portfolio. Market portfolio is basically almost like a mirror version of the market, but the market is where the assets and the returns are, so where the data, the raw data is, and the market portfolio is the signals. So maybe if I go to this slide, you see, so this would be what we'd consider as the market's data or markets where the data is, and this would be considered the market portfolio where the signal is, okay? So market portfolio is basically the whole processing that goes through after you get the data. The key goal in our case here, maybe not in general, but in our case here, is to produce a market portfolio that is a sequence of signals that maximize risk-adjusted returns. So we don't want to maximize cumulative returns. We don't want to maximize some other metric or even prevent tail risk. What we want in this case is maximize risk-adjusted returns, okay? Which means Sharpe ratio. So what is QuantNet? So based on the classification I showed you, QuantNet is sequential transfer learning using parameter transfer approach. That's what we're doing. We're going to try to leverage some insights from transfer meta learning community, incorporating multiple loss into a single network, so we can improve network regularization and avoid overfitting. Formulation is relatively simple. You have a market-specific encoder in a recurrent neural network formulation. In practice, we use LSTMs as the model. So we encode the returns and we encode, of course, the previous states of the encoder. Then we map the encoder through a transfer layer. And then after we did the encoder through the transfer layer, we map it back through a decoder. And to compute a trading signal is very simple. You just use a hyperbolic tangent because it's a function that's going to map things between -1 and 1, and that will generate the trading signal for you. Okay. That's basically the scheme, and you can see that the decoder is way more, let's say, focused on finding good signals that is going to try to maximize, in our case, Sharpe ratio, which is our loss function. And you can probably see this working out through the gradients. I'm not going to go into details, but I can come back. And the encoder in itself has to, of course, to balance not only the representation that it's going to give to the transfer layer, but also the quality of the decoder. But more importantly, how it's going to be the representation that's going to be done on the abstract level. Okay. The training is very simple. As you can imagine, you have a bunch of markets. You sample a mini batch of markets. You randomly select a window, so you can do the training for the LSTM through that window, because we're doing backpropagation truncated through time. You compute the encodings and the mapping through the transfer layer and the decoding for every market, compute the signals. Then you're going to compute the Sharpe ratio. Sharpe ratio is very simple formula. It looks different, looks strange, but it's basically this mu here is an average return. Average return, as you can imagine, you multiply the signal, the trading, how much trading you're going to do, multiply by the returns. So it's a multiplicative element. So you're multiplying S with RT, with this one over here. Okay, so you're multiplying both, and then you're averaging. You're summing, and then you're averaging. That's the average return. And this is what people would call volatility, which is basically the standard deviation. So you have an average, standard deviation. People would consider this even a t-stat or a z-score. That's what is called a Sharpe ratio. And for QuantNet, we compute a Sharpe ratio for every market, every asset, and then of course every market. And then you would just average across markets. That's what we're doing. Quickly, some results. As I told you, we managed, of course, that was not something that was planned, but we had a hint that this would pop up. There is a clear geoeconomic structure that emerged from QuantNet without receiving any such geographical information, funny enough. So when we look at the encoder of QuantNet and do a mix of a hierarchical clustering, etc., based on the encoding, we perceive that these markets over here of North America, like US, Canada, Mexico, UK, Germany, Sweden, and I'm just thinking, who is this one? The other one I forgot. Switzerland. All of these markets, they share the same traits, same characteristics. When you compare them, for instance, with France, with Spain, with Netherlands, Belgium, etc., they are also different from these markets, but they also share some commonalities. Brazil, some countries in the Middle East, Indonesia, some others in the Pacific, they have their own characteristics. And you can see this Asian bloc here emerging, China, India, Australia, and so on. So it was something that emerged. We didn't thought that would happen. Some of the clusters doesn't make much sense, like the green one. We couldn't understand it much, but in general, the picture looks was very interesting as one of the findings that we got. The other very important finding is the quality. So as I mentioned in the beginning of the slides, QuantNet managed to produce Sharpe ratios that were generally much better across a whole range of assets when we compare to simple structures like buy and holds, time series momentum, cross-sectional momentum, and his parity. As I managed, we managed to improve Sharpe ratios in the order of 50%, etc. When we compare, for instance, with cross-sectional momentum, was about 50% improvement, and so on. When we compare transfer versus no transfer, we have a mixed, we have an interesting feature. So the markets that benefited more, they had what we call positive transfer, were the bigger markets. So these markets over here, they're the ones where we were already performing well via no transfer, and we managed to get improvements. These markets over here, via no transfer, we're not performing really well, but we managed to get a boost. So there was a positive transfer. But these markets here, there was a mix that sometimes we managed to improve, sometimes we managed not to improve. And this region is probably one that we need to see how we can do things differently going forward. Final point, if we pick 4 big markets across the globe, S&P, UK in Europe, Saudi Arabia, Middle East, and KOSPI is Korea. Yeah, I think it's Korea. If we pick Korea, we can look at QuantNet results, and when we look at cumulative returns, it's clear that we are providing a way outperformance compared to all the other markets, compared to the no transfer approach. The markets that mostly benefited from transfer were small markets in terms of sample size. So if you have a very short periods of time when we're trading of data available, these were the ones that benefited mostly. When you have a medium amount of sample size, we were the ones that we didn't perform really well, but in general, we managed to outperform, provide better results when compared to the no transfer. And bigger markets, when you have a lot of assets, these are the ones that we managed to get good results in general. Again, just naming again, QuantNet, we applied it across 3,000 assets, 58 global markets. We managed to provide improvements in the order of 51% to 69% for Sharpe and Calmar ratios across a very traditional baseline in finance called cross-sectional momentum. We show the benefits of our approach when compared to no transfer one, having also improvements. As I mentioned, our key contributions are using a novel learning objective function, which is the Sharpe ratio, providing a novel architecture for transferring across trading strategies. This is the first one to do it. And we demonstrate that QuantNet can achieve significant improvements across global markets with an end-to-end learning approach. Just some acknowledgements. Thanks for my funding agencies. Thanks for the Allen Tree Institute. I did some of this research over there. Thanks for the UCL Center for Financial Computing for sponsoring myself. And you can find the link of the paper down here. Thank you very much.